Good morning everyone. Hope you are all good. Okay. If you have any doubts, please visit our school and then ask your doubts. Okay, and clarify it. Okay, to every teachers. Okay. And one more thing, please submit your classworks as well as test note within this 5th October. You'll see a lot of notes are there in the cupboard. So please submit your classwork as soon as possible. Okay, this week we're gonna learn or discuss about that heat effect. Okay, one of the best one. Here we have the 2 marks only theoretical. Heat effect. What is meant by heat effect? Whenever the current flowing through the conductor, consider this is a conductor. Okay, but exactly it is not a conductor. It is like a mica. Okay, so whenever the current flowing through the conductor, whenever the current flowing through the resistor, that current producing some thermal energy. Okay, that thermal energy producing some electromagnetic forces that also be known as the thermoelectric effect. But whenever the current flowing through the resistor, some of the energy are delivered in the form of heat and it is dissipated in the surroundings. So this effect we known as Joule's heating effect. And this law we known as the Joule's heating law. What is the Joule's heating law? It's nothing but, you know, what is the work done? The work done per charge will be equal to potential difference, right? Work done per charge equal to potential difference. The relation between the charge and the current. Current will be equal to Q by G. Amount of charges passing through per unit time. Then Q equal to IT. Now, then I can write work done will be equal to VIG. What is the relation between V equal to IR? Is nothing but your Ohm's law, right? So V equal to IR. We are substituting here IR IT. That work done I square RT. Okay, this is the work done which is done by the current and it is in the form of heat energy. Okay, it is in the form of heat energy. So heat developed in the conductor is directly proportional to square of the current and directly proportional to the resistance and directly proportional to the given time. Okay, so this is known as the Joule's heating law and there is lots of applications related to this effect. The first one is electric heater. Before that, turn page number 112 and example 2.27. Find the heat energy producing that resistance of 10 ohms. And when the current 5 ampere flows for 5 minutes. Current flows for 5 minutes. So 5 into 60. Okay. So 300. So how calculate that? Find the heat energy, right? So H equal to I square RT. H equal to I square RT. What is the I square? 25 into R 10 into 300. Right? So 7,500 into 10, 7,000. Okay, 75,000 kilojoules. That's it. 75 kilojoules. Right. Now listen. Applications of Joule's heating effect. Okay, turn page number 112. Electric heaters. The electric iron or electric heater or electric toaster are showing figure are some of the home appliances utilize the heating effect of the current. In this appliance, the heating elements are made of nichrome and alloy of nickel and chromium. Note it down. The nichrome is nothing but alloy of nickel and chromium. Okay, it has high specific resistance and heated to very high temperature without oxidation. Okay, it has very high specific resistance. Okay, the next one, electric fuses. You may see lot of electric fuses are made with the copper wire, right? Maybe the larger wire, which is more than 50 ampere. We have to use that copper wires, which is have the high specific temperatures. Okay. Okay. Copper fuses wire as we use, and then when the current is below 15 ampere, we can use lead and tin. Okay, lead and tin to provide the home appliance, to protect our home appliance. Why? Because whenever the excess of current flowing through the circuit, it may damage or it may affect the home appliance. So to break the circuit, we have to use lead and tin wire fuses. Okay. The next one is electric furnace. Electric furnace is maybe is a high temperature one, maybe up to 1500 degrees Celsius. Okay, nichrome wire and silica tube is used. Carbon arc furnaces are producing temperature up to 3000 degrees Celsius. Note it down. And next one, the electrical lamp. Okay, so the electrical lamp is made up of tungsten wire, right? So whenever the current flow through the circuit, it may produce lot of heat energy through the tungsten wire. So we can get the form of light by heating the filament. Okay, the tungsten filament melting point is up to 3380 degrees Celsius. Note it down. Okay, thermoelectric effect. The thermoelectric effect is nothing but conversion of temperature difference into the current or voltage, or the electrical voltage converted into thermal temperature difference. Okay, this is known as the thermoelectric effect. Okay, the Seebeck effect is very important. Whenever you just take the two different temperatures, like here it's a cold object, we have filled with ice cubes. So it's here the cold junction, and here we have that hot junction. Okay, here we have the water, boiling water or something like that. Whenever two dissimilar materials, what is meant by two dissimilar materials? Which is have the different chemical properties and different physical properties. Okay, whenever the two dissimilar materials kept on two different junctions, let it copper, and iron. When the two different metals are kept at the two different junctions, it forms a thermocouple. Okay, so the current always flow from copper to iron. Okay, when the two dissimilar materials, what is meant by dissimilar? It is nothing but two different metals which have the different properties of chemical and different properties of physical properties. Okay, that materials and that dissimilar metals are kept in the two different junctions, which forms a thermocouple. Whenever the EMF developed in the thermocouple, it is called thermo EMF. Due to the thermo EMF, the current is developed and current is flow through the thermocouple. It is called thermoelectric current. This effect will be known as the thermoelectric effect or Seebeck effect. Okay, so remember this. Thermocouple producing the thermoelectric current. Okay, so whenever the EMF developed in the thermocouple, it is called thermo EMF. Due to the thermo EMF, the electric current produced in the circuit, it is called thermoelectric current. Okay, so what are the applications of Seebeck effect? There is a lot of applications in the Seebeck effect. The first and best one is the thermoelectric generator. Okay, and you may see a lot of thermal power plant in our area, around your area. All the thermal electric power plants are working on the principle of Seebeck effect. And the second one is automobiles. Okay, automotive thermoelectric generator, increasing that fuel efficiency, and using the thermocouples or thermopiles. Okay, to radiation, measuring that radiation level. Next one thing, Peltier effect. This is one easier one. What is the Peltier effect? When the two the dissimilar metals are kept in the two different junctions, okay, the current evolve at one junction and absorb at other junction. That is called Peltier effect. Okay, what is the Peltier effect? When the electric current passes through the circuit of the thermocouple, heat is evolved at one junction and heat is absorbed at another junction. In copper and iron, okay, when it's placed in the metal at the same temperature, the current from the junction A, current flow from copper to iron, and the heat is absorbed at the junction A, becomes cold and B becomes hot. Okay. Next, the Thomson effect. Okay, this is very important one. Two more questions. What is the Thomson effect? There are three models used by Thomson. First, he take copper wire. Okay, copper rod. When the copper rod, the middle of the copper rod was heated by high temperatures. Okay, let A and B be the points. Here, the current enters into the conductor rod in this directions. Okay. When you are taking this, let A, M, okay, whatever A, M, AC, right? AC and B. So whenever the current flowing through the copper rod, which is the middle point, is having the higher temperature, at AC heat is absorbed and that CB heat is evolved. Okay, for the copper rod. For the iron rod, okay. Whenever the current flow in this direction, let A, B, C. At A, B same middle point is heated by high temperature. At A, B heat is evolved and BC heat is observed. Okay, so this is how they have the different for the different metals and the different types of metals. Lot of temperature difference are producing the current. This thermoelectric works on the principle of the Thomson effect also. For lead, okay, for the lead, there is a null Thomson effect or nil Thomson effect. Whenever we are taking the lead rod, whenever you are applying the current or external field with the middle point is high temperature, there is no changes in the thermal energy. There is no changes in the temperature. They maintain at the same temperature. So this effect is called as null Thomson effect or nil Thomson effect. Okay, the Thomson effect will be 0. So we came to conclusion of this lesson. Second lesson is called nothing but current electricity. Current electricity. Whenever the charges are in the moving or in the motion, it is called current. Okay, amount of charges passing through the given area or cross-sectional area per unit time we called as current. Okay, then I equal to Q by T. What is the SI unit of this? Ampere. SI unit of the current, ampere. Okay. Second, what is meant by drift velocity? The drift velocity is nothing but some free electrons are drifted towards the positive terminal of the conductor. Positive terminal of the conductor are drifted towards the positive terminal. That average velocity we known as the drift velocity. So the drift velocity is nothing but the collision time of the acceleration. Acceleration into collision time. Okay. And third one, what is meant by mobility? The mobility is nothing but what? The drift velocity occur per unit electric field. Occur per unit electric field. So mobility is nowadays given by letter mu. Drift velocity per unit electric field. So what is that? Meter per second inverse, volt inverse. That's it. For electric field, volt inverse, velocity meter per second inverse. The fourth one. What is the relation between the drift velocity and the current? Drift velocity and the current. All the conductors, almost all the conductors conduct the current, they allow the charges to pass through it. But Ohm's discovered that there is some resistance, there is some resistivity opposite charges which is moving from the positive to negative terminal. That we call as resistance. Before that, what is the relation between the current and the drift velocity? That I equal to NAE VD. Okay, that current which is nothing but your drift velocity. Okay, and the fifth one, what is the relation between the current density and the drift velocity? So current per unit area, it is called current density. So which is equal to NEVD. And the sixth one, what is the macroscopic form of Ohm's law? Okay, J equal to sigma E here. Sigma is called conductivity. The reciprocal of the conductivity is nothing but your resistivity. Reciprocal of the conductivity is nothing but your resistivity. So we can write also current density will be equal to sigma E. Okay, and what is mean by Ohm's law? When the potential difference across the conductor is directly proportional to current developed in the conductor. Okay, V is directly proportional to I. So whenever you are taking V equal to IR. R is the resistance which opposes the motion of the charges. Okay, the eighth one. The other form of Ohm's law, and what is meant by resistance? Which is opposite charges to moving. That resistance is directly proportional to resistivity. Okay, resistivity will be equal to RA by L. Okay, then resistance will become L by OA. Is directly proportional to the length and inversely proportional to the resistivity. That resistivity, 1 by resistivity is nothing but conductivity, right? So conductivity and then area. Okay. So next one thing. After this one, Ohm's law, we saw that resistance in the series. Okay, resistance in series and parallel. So Rs will be equal to R1 plus R2 plus R3. Whenever they are in a parallel, 1 by Rp will be equal to 1 by R1 plus 1 by R2 plus 1 by R3. Okay, so 12th one is nothing but cells, right? So equal resistance and Kirchhoff rule. The Kirchhoff rule is nothing but what? Kirchhoff rule is nothing but there is two rules. The first one is called junction rule. Second one is called voltage rule or current loop rule. Okay. The junction rule or current law. What is mean by current law? Is nothing but algebraic sum of the currents meeting at the junction. Meeting at any junction will be equal to 0. Meeting at any junction will be equal to 0. Current entering to those junction will be equal to current leaving the junction. Current entering the junction will be equal to current leaving the junctions. Okay. And the next one. What is that? The voltage rule. Algebraic sum of product of current and the resistance in the closed circuit, which is will be equal to the EMF in the closed circuit. Okay. So that also we know. After that, came for temperature dependence of resistivity. Temperature dependence of resistivity. That is nothing but alpha will be equal to RT 1 of T minus T naught into R. Okay. So next one thing. Based on this Kirchhoff law, Kirchhoff rules. Okay, first rule. Kirchhoff rule. The 13th one, Wheatstone bridge. So what is mean Wheatstone bridge? To find that unknown resistance, right? To find that unknown resistance. There is a three copper strips which is made the L shape, and one is the long strip. There is like a AB which is connected with the magnetic wire. And so on. We know. Okay, Wheatstone bridge, one of the best applications of Kirchhoff law. It is nothing but P by Q will be equal to R by S. P by Q will be equal to R by S. Okay. The next one is nothing but meter bridge. What is that? Meter bridge. So based on this also to find the what is that? Unknown resistance. Based on the length we can find P by Q will be equal to L1 by L2. Okay. The 15th one is nothing but cells. Cells is the EMF which is developed in the across the conductor. The internal resistance also there. The resistance offered by the electrolytes or internal battery or battery by the battery or by the cell is called internal resistance. Okay. So potentiometer is one of the main applications. Is nothing but the EMF developed in the conductor is directly proportional to balancing length of the potentiometer. EMF developed in the battery or cell, it is directly proportional to balancing length of the potentiometer. Okay, so write all those 15 and these are very little bit important. Okay, so just remember all those things whenever you are seeing these equations. Okay. The next one will go for the third lesson. The third lesson is nothing but your magnetism. What is that? Magnetism or magnetic material. Before that, we must know what is the magnets and what are the magnetic properties. Okay, magnetism and magnetic effects of electric current. Magnetic effects of electric current. Okay, magnet, no doubt. Start with your lesson. Okay. Everyone is likes the magnet, which is very attractive. When we are in childhood, we love to play with the magnets. We love to play with the iron fillings, right? So why and where, how the magnets are discovered? The first one, the country of Magnesia, I think, is kind of island. Okay, there was one shepherd. He using through that irons, horseshoes, right? They are using the horseshoes which is stick on the rock which is never coming out. Okay, they felt something was attracted that iron which is called magnet. From the word it came from magnesia, right? So there is a lot of uses by using this magnet, right? So electromagnetic train, and then MRI scans, and then based on speakers. So one of the main applications are these headsets, that means Bluetooth devices. When you are comparing, see, this also there is a magnet which is North Pole and South Pole. Stick it, right? See, there is a North and South Pole, right? So they will attract each other, and then these are the magnets which is we can use day to day life, but we doesn't know whether they are inbuilt with the magnet or not. That's it. That's a problem. So magnetism is one of the greatest one. Where we are getting this kind of magnetism? Inside the earth or outside the earth? We first discuss what dynamo effect, not the magician dynamo. It is a dynamo effect which is given the statement of the inner core of the earth have some molten state of ions or nickel and aluminum, whatever may be the minerals which is inside that earth. they are in the molten state. Okay, so they providing some amount of field lines around that earth, which is we called them as magnetic field lines. Okay, so before that, the earth is like a okay, here the north pole and we have the south pole. Here we have north pole and here we have the south pole. Okay, so this is called exact north and south pole, right? This is called true north or true south. True north or true south. When you are suspended some needles or when you are suspending some what is called bar magnet. Okay, when you are suspending some bar magnet or freely suspended needle, it always attract towards the north pole and then south pole, right? So which is exactly not exactly which is on this side. This is your magnetic meridian. This is your magnetic meridian. This is your geometric meridian. Geometric meridian. Okay. Listen. This is your exact north and south pole. When you have freely suspended needles or bar magnet shows this kind of deflections, which is called geometric meridian. The angle between the magnetic meridian and the geometric meridian in the vertical scale, which is called declination. Declination. Okay. So remember, the angle between the magnetic meridian and geometric meridian. The magnetic meridian is nothing but exact north and south pole of the earth. Okay. The geometric meridian, which is we call them as the freely suspended bar magnet, that's always attracted to a south pole or north pole. Okay. When you are freely suspended, it will show the north and south pole only. So whenever it shows the north and south pole, it's not exactly north and south pole. It's some deflection there is. Okay. There is some deflection which will occur. That angle between these two things we call that declination. See, for example. In Chennai, in around Chennai, there is a uniform magnetic field. But around the earth, it is not uniform. It's a non-uniform magnetic field will be surrounded by our earth. But whenever you are taking that laboratory, whenever you are taking in around in Chennai or some other places, district or Chennai or Delhi, whatever maybe Trichy, Kanyakumari, or Uttar Pradesh, Madhya Pradesh, whatever maybe. They are taking the magnetic field and their laboratory as a uniform magnetic field. Okay, so in equator side or pole side there is a lot of difference between the magnetic fields. So there is also magnetic field science caused by every day it was affected by the cosmic rays also. Okay, you know auroras and asteroids, right? Okay, I'll show. See, the other side, the horizontal direction, right? The horizontal direction, whenever there is an horizontal direction, when you suspended the freely magnetic material or freely bar magnet or freely suspended needle, it shows some deflected horizontal area. Okay, the angle between the geometric meridian, that is in the horizontal direction, and the total magnetic field in the horizontal direction, that angle between these two things we call inclination. Inclination. Okay. Next one thing, in the horizontal component we have taken as that BH. Okay, horizontal component, the magnetic field we can take as BH will be equal to B cos I. Okay, in vertical direction we can take BV will be equal to B sin I. Okay, whenever the vertical we can take this ratio, which is will be equal to cancel tan I. Okay, so here we have to note whenever that magnetic field is parallel to the surface of the magnetic field, surface of the earth. Whenever the magnetic field lines are parallel to that surface of the earth, then theta equal to 0 degree, then BH will be equal to BE, then BV will be equal to vertical magnetic field will be equal to 0. Okay, whenever that magnetic field lines are perpendicular to the surface of the earth, theta will be equal to 90 degree. So BH, that means horizontal magnetic field will be 0, then vertical magnetic field will be equal to magnetic field. They have the magnetic field. Okay, so this one we can write as the magnetic field at the equator. Magnetic field at equator. Night and day are come across this magnetic field, and also asteroids and auroras. Okay, the North, Antarctic and Arctic. Okay, Arctic side or northern side or southern sides are forming the every year and the frequently. Why? Because the Earth is surrounded by the magnetic field, right? Earth is surrounded by the magnetic field lines. Thus, magnetic field lines always start from the North Pole and they terminate at South Pole. North and South Pole. Okay, so whenever the cosmic rays are enter into the equator, whenever the cosmic rays are enter into the equator, they enter perpendicular to the magnetic field, so they are deflected by this magnetic field. They are deflected by this magnetic field. When they are entering to the north pole, cosmic rays, okay, whenever they are coming out from the space, they are entering to the north pole, they are highly interacting with the high atomic particles and then in the atmosphere. That's why they are showing some other legs in the northern region and southern region. They can easily enter. They are parallel to the line, so they can easily enter. So they will highly interacted with the atomic particles or atmospheric particles, and then they show that energy will convert into the light. That light will show the different colors. Okay. For example, the pale yellowish green color is produced when the ionized gas takes past collision, and the blue and purple red aurora is produced due to the ionized nitrogen molecules. Okay, ionized nitrogen molecules. Next one thing, the properties of magnetic field lines. The properties of magnetic field lines. Magnetic dipole moment. Whatever you are learned in the first lesson, it came in this lesson. Okay, it will come in this lesson also. What is the dipole moment? Okay, what is the magnetic dipole moment? Okay, listen. This is the bar magnet, right? Here the bar magnet. Here we have the poles, north and south pole. North and south pole. This length we can call this. Okay, this length we can call geometric length. This length we can call geometric length. Okay. This length we can consider, or this length we can take as magnetic length. Magnetic length. What is the length of the magnet? It's nothing but the distance between the poles. Poles distance. The distance between the poles we can call them as magnetic length. The distance between the edges we can call them geometric length. Okay. The properties of magnets, type of magnets, there is a lot of things. First one thing, there is a two type of magnets. First one is the natural magnets and then artificial magnets. What is mean by natural magnets? Natural magnets occur within nature, but which are the weak magnetism or weak magnetic field. But artificial magnets are made of copper, nickel, and iron. Okay, aluminum and all the mineral ores are mixed together, and then they will make that artificial magnets, which is very powerful magnets. Is called neodymium magnet, right? Okay, and after that only the electromagnets. Now listen. Neodymium magnets, whatever with artificial magnets will be have the more powerful magnets. Okay, we can make any other shapes of the magnet. Okay, the properties of magnets. The properties of magnets is nothing but the freely suspended bar magnet will always point along north and south pole. Okay, freely suspended bar magnet always pointing north and south pole. The north direction attract towards the south, and south direction will be attract towards the north pole. Okay. The attacks or repulse of the another magnetic substance are another towards itself. The attractive or repulsive force is maximum near the end of the bar. Okay, the attractive forces will be maximum at the edges or end of this bar magnet when compared with the centers. When the magnet is broken into the lot of pieces, each pieces having the north and south pole. Pieces having the different poles. Okay, and then the two poles of magnet have the pole strength equal to one another. Two poles of the magnet will be equal to one another. Okay, here what is the magnetic dipole moment? The magnetic dipole moment is denoted by Bm. Any one of the pole strength and then distance between them. Any one of the pole strength and the distance between them. The length of the bar magnet is called geometric length, and the length between the two magnetic poles in the bar magnet called magnetic length. The magnetic length is always slightly smaller than the geometrical length, and the ratio of the magnetic length will be equal to 5/6. Okay. And then magnetic field length. What is meant by magnetic field length? Remember that the magnetic field lines are always coming from north pole to terminate at south pole. They are coming from north pole to south pole. They never intersect each other. And then whenever you have drawn the tangent on the lines, it gives the direction of the magnetic field. Okay, direction of the magnetic field. And when the magnetic lines are closer to each other, then the magnetic field will be maximum. When the lines are far away from each other, the magnetic field lines are minimum. Magnetic field lines are minimum. Okay, the next one thing, magnetic flux. Whatever things you have learned in the first lesson come in the magnetic. That's all in the electric field. Same like this for magnetic field, right? So magnetic flux. What is meant by magnetic flux? It's nothing but the number of magnetic field lines passing through the given area. Passing through the given area or any area through the area. It is called magnetic flux. Okay. Pi b. Okay. Here we have to deal with the pi b, which is called BA cos theta. Which is called BA cos theta. There is EA cos theta, here BA cos theta, magnetic flux. Number of magnetic field lines are passing through the given area. Number of magnetic lines are passing through the given area. It is called magnetic flux. Okay. Whenever the theta is 0 degree, then it will become maximum flux. Whenever theta equal to 0 degree, pi b will be equal to maximum. Whenever theta equal to 90 degree, the magnetic flux will be equal to minimum. Okay, minimum are 0. Next one thing, what is mean by uniform magnetic field or non-uniform magnetic field? They have the same direction and the same magnitude. Okay, they have the same direction and same magnitude. It is called uniform magnetic field. If they have the different direction and the different magnitude, then it is called non-uniform magnetic field. Non-uniform magnetic field. Okay, the Coulomb inverse square law. The Coulomb's inverse square law. What is mean by Coulomb's inverse square law? This is nothing but the force of attraction or repulsion between any two poles. Okay, any two magnet force of attraction or repulsion between the any two magnetic poles is directly proportional to product of the strength. Okay, product of the pole strength and inversely proportional to the square of the distance between them. Okay, the force of attraction or repulsion between any two magnetic poles is directly proportional to product of their pole strength and inversely proportional to square of the distance between them. Fm will be equal to K QMA QMD grouped by R square. So what is mean by K? K is nothing but constant. Coulomb constant is nothing but mu naught by 4 pi. Mu naught is nothing but permittivity in free space. Okay, what is the value of mu naught? Mu naught will be equal to 4 pi into 10 power minus 7 Henry. Okay, 4 pi into 10 power minus 7 Henry per meter. Henry per meter. Okay. So next one thing. Example 3.15. The repulsive force between the two magnetic poles in air. Repulsive force will be equal to 9 into 10 power 3 Newton minus 3 Newton. Okay, if the two poles are equal in the strength and separated by a distance of 10 meter, calculate the pole strength of each pole. Okay, calculate the strength of the each pole. So they are given the distance R will be equal to 10 centimeter. Okay, we have to calculate what is the pole strength. That's it. Okay, QM square. So F will be equal to K QM. So it is nothing but QM square by R square. So F R square by K will be equal to QM square. What is it here? 9 into 10 power minus 3 into 100 into 10 power minus 4 divided by K. What is the value of K? Mu naught by 4 pi. Mu naught by 4 pi. 4 will be cancelled. So it is 2 into 10 power minus 7. 50. So 5 into 450. 5 is 450. 450 into 10 power minus 7. Here 10 power minus 1. 7 cancelled. So what is our answer? 450. I mean 9 into 10 power minus 3 into 10 power minus 7. 5 into 30. That first square by right. Just give an answer. Okay. 9 into 10 power minus 3 into 10 power minus 7 and 30 Newton per Tesla. See, the next one thing, It's nothing but magnetic field at a point along the axial line and equator line. Same what we have did in the electric dipole due to the electric field in an axial line and equator line. Same thing. Okay, we'll do in the next class, inshallah. Okay, guys. For this week, just remember what is mean by heat law or heat effect, and then what is mean by Thomson effect or Peltier effect. Okay, heat at developed one section and heat is absorbed another section. Okay, and then what is mean by magnets, types of magnet. What is mean by different declination and inclination. What is mean by Coulomb signal square law, and then what is that? What is mean by magnetic flux? Okay, these are little bit 2 more questions, and inshallah next week onwards we'll finish this lesson. Okay, thank you guys. Allah Hafiz.